Okay, so today we're going to start talking about radicals in your Math Interactive Notebook. That's going to start on page 72, and hopefully we're going to cover up through slide 77 today. So we're going to start with the TOC. There is going to be one slide, this first slide, that I'm going to actually send out to you as a separate attachment. I'm going to need you to copy that and put that into your Math Interactive Notebook digitally. I will show that how to do that in class on Thursday, as well as how to do that in class on Friday for the remote students. So TOC for today, table of contents, is what are radicals for slides 72 through 75, and review prime factorization, slides 76, 77. And in my notes, that's going to be pages 14 and 15. So go ahead and write those in your TOC. Then once you're done with that, I'm going to write the notes on a separate piece of paper here to make it a little bit easy. So imagine this is page 14. And we're going to write, what are radicals? Okay, so what are radicals? Okay, so a radical, often called a root, and that's because it's a computational expression that uses a root. The official math definition is an nth root of a number is the number f which, when raised to the exponent n, equals the number. So an example of this would be, if we're looking at the square root of 25, square means value of 2. Because we know 5 times 5, or 5 to the second power, equals 25, this equals 5. And as we go through more explanation, it will become clearer. So first off, what does a radical look like, right? A radical is put under a radical sign. Your radical sign typically looks like that. It may just be a check mark. You may not see the top part of it, depending on like the computer system that we're in. Over here, we have what's known as the index number. Okay, what's underneath, and we can call this n. What's underneath, we're going to call this letter A. We call this the radicand. And This is the radical sign. And notice in the definition, we use the word computational, right? So up until this point, you've known how to add, subtract, multiply, divide. And we've also talked about exponents, right? Well, in math, everything's symmetrical. Everything has an opposite. So addition and subtraction are inverses. Multiplication, division, inverses. We just studied exponents, and now we're studying radicals or roots. And that's because radicals and roots are inverses to one another. So we're going to talk about what a radical is. So the radicand is an expression under a radical sign. Right, and it's that value being taken to the nth root. And the index number tells us the number of identical factors needed for the root to come out of the radical sign. So with an exponent, it showed us how many times a base number should be multiplied by itself, whereas an index number is going to tell us how many times a factor must exist under the radical sign in order for it to come out. So we're going to be digging back to some of the things we learned in 6th grade about prime factorization. So how do we use or say the word root, radicals, etc.? How are we going to talk about it in words? So first off, this is our radical sign, and make a little, here we're going to call this the symbol. What the words would be. And a quick example. So this symbol would be a square root. So similar to like when we don't see an exponent, we assume it to be 1. So no index number assumed to be 2. Okay. And we can have a cubed root. We can have a 4th root. Okay, etc. 5th root, 6th root. So an example. So the square root of 4, right? 4 is the same thing as 2 to the 2nd power. Our index number, we don't see it, so we assume it to be 2. So it's telling us that we need factors, at least 2 factors that are identical for it to come out. Here, 2 exists twice, it gets to come out once. Kind of like roots growing a plant. Here, if we look at the cubed root of 8, well, 8 is worth 2 to the 3rd power. So this is telling us how many identicals we need. We have three 2's underneath here, so 2 gets to come out again. We keep on going. So a 4th root of 16, right, just kind of write this in expanded form. This would be the same as 2 times 2 times 2 times 2. In other words, 2 to the 4th power. So 2 would get to come out of that. Okay. Within that, we have things that we call perfect square numbers. One way to look at this is the square root of 25. Right, so we write that as like that, is 5. Because 5 times 5 equals 25, right? Index number 2, 5 exists twice. The reason why we call it a square number is if we look at a square, right, the parameters of being a square is that all the sides of a square are exactly the same length. So here we can see we have a square that's 5 units on each side. The way we find the area of a square is to multiply side times side or length times width because it's part of the rectangle family, and that equals 25. So that's why we call it a square root, because we're looking for identical factors, a set that contains 2. And here, the way you find a square, the area of a square, is side times side, which those have to be identical factors. If we looked at something like a cubed root, and I'm horrible at drawing 3-dimensional figures, so sorry, actually, so ignore that one side. But imagine if we had a side of 5, a height of 5, a width of 5. For the cubed root, a cube is a 3-dimensional representation of a square. So imagine like a dice, right? We're saying that side times its height would have to be the same thing. That's how we find volume, right? And for volume, the units of measurement with that would always be cubic units. So that's where we get the cube root, which means 3. And in this case, we know that the cube root of 125 is 5 because 5 times 5 times 5 equals 125. Okay? And in order to be considered a perfect square number or a perfect cubed root, that means we're looking at numbers that work exactly. So like when you think of a square, right? We have graph paper right here. We know that in order to be a square, the sides have to be equal. So think about that. I can draw a square that has an area of 1, right? This is worth 1 unit. This is worth 1 unit. 1 times 1 is 1. We can draw an area of a square that has an area of 4, and each side is worth 2 and 2. We can draw one that is 9. Because 3 times 3 gives us 9. So numbers like 1, 4, 9, 16, right? I know this area is 16 because 4 plus 4 plus 4 plus 4, or 4 times 4. And then we drew a 5 by 5 square. So these are considered the perfect numbers: 1, 4, 9, 16, 5, because they have integer side values that when multiplied together give you another integer. If I asked you to draw a square with an area, not a side length, an area of 2, it would be really hard to do, because looking at this, I would need something that's bigger. The length of it would be bigger than 1, and the height would be bigger than 1. And most likely this is not going to be an integer number, because we already know 1 times 1 is going to give us 1. 2 times 2 is going to give us 4. So in order to get an area of 2, I would need a number that's between the numbers of 1 and 2. So that would not be an integer number. In fact, that would probably be a never-ending, non-repeating number, right? That's an irrational number. So when we are looking at non-perfect numbers, if you're taking the straight decimal of trying to figure out the length of the side of the square, it would be an irrational number. But we're going to see that later on, we're still going to be able to simplify those in radical form. Because for mathematicians, one of the most important things is to be accurate, to be precise. That's why they would prefer fractions over a decimal that has to be rounded. That's why we use radicals, because we want to give the exact measurement of something versus an estimation if we have to try to turn that into a decimal. Because if it's a never-ending decimal, there's no way to represent that, writing it down, without rounding the decimal. Because if it's never ending, we would still be sitting here just constantly writing it, right? Like it's never ending, it's never going to stop. So that's one way that we use radicals, is to provide a measurement or of something, and we want it to be exactly accurate. Okay, so that is what are radicals. In your slide deck that you have a page which asks you to fill this in, but then I want you to go ahead and fill in the perfect numbers. And I want you to look at perfect square numbers as well. So if I looked at the cubed root of 1, well, I know 1 times 1 times 1 would give me 1. So this is going to be 1. The cubed root of 8, we've already done. We know it's 2. Cubed root of 27, 3. Okay, so I want you to fill out these commonly used perfect numbers and perfect square numbers in your slide deck. Okay, so that is kind of what is a radical.